Hi and welcome back. In the last lecture we deal with countable spaces. So this time we'll be dealing with uncountable spaces. So uncountable spaces are those in which the omega is an uncountable set, just like real numbers. So there cannot exist a bijection between uh, the set of natural numbers and omega. So what I'm saying is the set of natural numbers is not enough to uniquely tag each element of omega. That sort of thing is not possible there. Okay, so in this lecture I will present a special case of what will happen if omega is the set of real numbers and what sort of problems we face while assigning probability measures to its elements or subsets. Okay, so probability is basically a measure over omega and its subsets, and it encounters some problems when we deal with the subsets of R, because there do exist some subsets of R for which no consistent measure is there. So for example, if I would encourage you to look at something called the Vitali sets. So Vitali sets are those which are gotten by partitioning 0 to 1 and then choosing a representative element from that partition. So it so happens that in that Vitali set, it cannot be exactly measured, although it's a proper subset of omega, but it's a proper subset of the real numbers, but it cannot be measured, and so probability cannot be exactly established for all possible subsets of the real numbers. And so my point being that 2 raised to r, that is a power set of real lines, is a Borel field. It's a Borel field of sets, but not all elements are measurable. They will eventually lead to contradictions when you're dealing with countable additivity and all those things. And so what I propose is an alternate construction. Instead of considering all the uh, subsets of reals, why not consider only the the Borel field which is formed via the open intervals and its countable unions and intersections. So what exactly does the countable union and intersection consist of? That's what I'll be showing you. So the first thing is it'll consist of these sort of things. So sorry, I meant closed intervals, not open intervals. So suppose you have closed intervals and you take the you take the countable intersection and unions of them. What exactly will you get? One is you will get other uh, closed intervals. You will get a collection of closed intervals. Like if you have this is a closed interval, this is another closed interval. You take the union of that, you will get two closed intervals. So these sort of things are there, but there is more. You have x less than xi. So basically, a whole half of the real line. That sort of thing is possible. And similarly, you have this side of the real line as well. That is also possible. Open intervals. You can get open intervals, in fact. Open intervals is also a valid element in this Borel field. And last but not least, single points. Yeah, these things are there. Now, some of the subsets of R, for example, that Vitali set, they don't fall into this Borel field. Yeah, I know it seems pretty counterintuitive, because what exactly have I missed out here? Well, I have missed out a few things, but those subsets are actually not relevant in practical applications, so we can just ignore those. Just know that the Borel field I'm forming is via the unions and intersections of all possible closed intervals, and it will give you open intervals, it will give you these half lines, it will also give you single points. So I mean, what else do we need? Okay, now how exactly will we construct a probability measure on these intervals? So again, the number of intervals in the real line, a lot of them exist, uncountable number of them exist. So how exactly will we get ourselves a probability measure? Okay, so one of the uh, ways to go about doing this is consider any function alpha of x. So alpha of x, it takes in a value from the real line and it outputs another number. And what it satisfies is, if you integrate alpha of x over the whole real line, it will be 1. Alpha of x will be greater than or equal to 0 for all real x, And the probability of A, if A is an event, A is belonging to the Borel field we defined above, then the probability of A is the integral of alpha of x over A. So A is a subset of the real lines, okay? So I mean, you can integrate over any subset of real line. That's not a problem. Now, does this sort of probability measure even satisfy um, the axioms of probability? Let's see. So the probability of A is obviously greater than 0. Why? Because alpha of x greater than or equal to 0. So we cool there. The probability of omega, that is the whole real line, is 1. Again, I have defined it up here. Now, if A and B are two disjoint events, then the probability of A union B is obviously the integral over A and A union B. So for example, consider this. Consider two intervals. I'm integrating over two intervals, both of which are disjoint. And so in this case, I can actually split the integral into integral over this plus integral over this, because there are no common overlapping elements, right? And so I can do this. It's actually pretty easy to do. And now that integral over the individual intervals will basically be the probability over that interval, and hence I have basically proved the additivity axiom. Okay, now to get to some good results, what if I want to take the probability of this sort of thing? What is the probability measure of this sort of interval? Half open, half closed. Well, turns out this thing can be written as, well, uh, sorry, minus infinite to x2 closed minus x1. And obviously I'm assuming that x1 is less than x2. Okay, and so this way that will give me p of x less than x2 minus p of x less than x1, and that over here will basically be the integral of x1 to x2. Obviously, I mean, I needn't do all these things. I could have just, you know, written it as the integral there itself. But if you set things up this way, then look at this. As x1 tends to x2, this half closed, half open interval will basically approach a single point, which will be x2. And so the probability of a single point, what will it be? The probability of a single point is, well, 0, because this integral will become 0 in the limit. And so that way the probability of single points are 0. But what is this? If the probability of each single point is 0, how am I getting non-zero probabilities for intervals? Again, the whole reason is uncountability. That is the reason. Things get a bit weird when we deal with uncountability, and so that's why we are assigning probabilities to intervals, and that interval is the probabilities are, well, calculated via this alpha of x function that we are free to define on our own. But now the point is, single points will have 0 probability. But in real life, how often do we deal with, just I want the probability of a single point. So if I have a signal, I want to know that, okay, what is the probability that it will take exactly this value? We don't want that. In general, electronic systems have a tolerance, so they can handle values between here and here. So what I want is, what is the probability that my signal value at this time will be between these two values? It will lie in this interval. That is the sort of things we are concerned with. And so that's why this framework of probability is used when we are dealing with real numbers. Alright, with that I'll end my lecture on countable and uncountable spaces. Alright, see you next time. Stay tuned.